Let's recall what analysis is. Our starting point was a set of requirements that treated the system to be developed as a black box. The requirements specified what the system should be able to do. It specified what information the system should be able to remember. But it didn't get into any details about how the system did it. The requirements could not specify anything inside the black box. Our job in analysis is to figure out what's inside the black box. Now, the difference between analysis and design is that analysis is a discovery process. You identify what needs to be implemented. The design describes how those things are implemented. The design is a model of the code, while the analysis model is more of a detail of how those requirements will be met in terms of the things inside the system. So the analysis is a discovery process, identifying the classes of interest that are inside the system. Remember in our discussion of OO principles, when they invented object orientation way back in the 1960s, they were trying to do simulations. And so object-oriented systems are very good at simulating things in the real world through the use of objects and classes of objects. And so we identify the things that need to be simulated in our OO analysis, and we're going to implement those in terms of classes. So we identify the classes, we identify the attributes of the classes, we identify the operations of those classes, we identify relationships between those classes. Relationships actually would most likely be object relationships rather than class relationships. Things such as associations or aggregations. Those are relationships between the object instances of the classes. But we would draw those relationships on a class diagram, a UML class diagram. We just elevate those relationships up to the class level for our diagramming purposes. We model the dynamic relationships, or dynamic behaviors of the objects. So when we describe the behavior of the system in the requirements level, we say the system receives a message and performs some operation. Well, when we're doing our analysis, our OO analysis, we say, well, when the system receives that message, which objects are required to perform their operations, in what order do the objects perform their operations. That's the dynamic behavior of the system. We could also then focus in on each individual object and look at and study the state-related behavior of the objects using state transition diagrams. So the OO analysis process starts at the requirements level, the black box level. Our first goal is to find the candidate classes. And there are lots of different techniques for doing this, but most of them involve some understanding of what objects are. That's why we talked about the object-oriented principles earlier. You have to understand what objects are and how we simulate the real world in terms of those objects. We could use the scenario-based descriptions of the requirements, maybe use cases, things like that. You could also use something called CRC analysis. CRC stands, the acronym stands for Class Responsibility Collaborator. You can look that up, Google that if you want to find out more information about CRC analysis. It's a very useful technique, been used for years in doing object-oriented analysis. And it's a good way, it's a scenario-based technique for discovering the behaviors and the attributes of the classes. We show the relationship between the classes, static relationships, and in a class diagram, and then we show the dynamics of when the system does things. We show how those objects collaborate to perform those operations. We can use various dynamic models in UML, activity diagrams, interaction diagrams, state models. So when we're trying to find the candidate classes, this is the number one goal here in analysis, is to find what are the classes, what are their attributes, what are the behaviors. Okay? We're trying to model, remember, they're trying to model the requirements of the system from the inside. So we're flowing the requirements, the black box view, down to the individual classes. Okay? Now, we're not trying to implement those classes at analysis. We're not trying to show how the code works. That's the purpose of design. So what we're doing is specifying the classes. to be implemented ultimately by the design and then the coding. So where do we find the candidate classes? How do we go about finding the candidate classes? There are lots of different techniques. Here are some suggestions about what to look for. The primary thing that I look for is I remember the purpose of classes or objects is to hold on to information, encapsulate information. So I ask, well, where is the information, or what is the information? First of all, what is the information that the system needs to retain? And then I make decisions about, well, how am I going to encapsulate that information? How am I going to chop it up into meaningful, cohesive objects? Okay? So the purpose of an object is to encapsulate information in a cohesive way. So all information related to one kind of thing is encapsulated in one object. Information about something different is encapsulated in a different object. Okay? And then I think, well, in terms of that information that is encapsulated within an object, what kind of behaviors do these objects need to support in order to provide behaviors, functions or operations on that information? Okay? To set the information, to retrieve the information, to update the information. Okay? So we have to identify the operations. Objects in the problem space hold information and operations pertinent to the problem domain. And what does that mean? It means that at analysis time, I am not going to identify objects and classes of objects that are needed only in the solution space. Things such as tables or collection objects or user interface objects, unless I see them in the problem domain. Okay? So what I'm trying to do is I'm trying to simulate the problem. I'm trying to simulate the things in the real world in objects. So identify the classes of objects that if you went back to the customer, to the stakeholders, and said, here's my list of candidate classes of objects, if they would recognize them, then that's a good set of candidate classes of objects. If you're getting down to computer implementation kinds of objects, you've gone too far. You've gone down to the design level, right? And so the set of classes that you come up with at analysis time should be recognizable by somebody that didn't know anything about classes, didn't know anything about programming, software or computers or anything. A problem space expert should be able to recognize the things in the problem if you present that list of classes to them. Some other heuristics. Objects are like little people. We can use anthropomorphism. That's a great word, anthropomorphism. It comes from the Greek, means human shape, human form. Okay, the objects take on human forms. In other words, objects respond to messages. Humans respond to messages. Requests for service. They send messages to other objects. That's how they collaborate. Well, that's how humans collaborate. And the objects change their own state only in response to events, to messages arriving. Well, humans do the same kind of thing. So if you can sort of think of these objects as little people sitting inside your computer and talking to each other, sending messages to each other, and controlling their own state, their own data, that might not be a bad way to think of the object-oriented analysis model. And as I said, I think of objects as persistence mechanisms. The purpose of an object is to hold on to information and perform all the updates on that information, all the operations on that information. And so we're modeling the problem in terms of these objects. So another thing to think about is every piece of information is encapsulated inside some object, and probably only one object, right? Every piece of information is probably encapsulated within one place, probably not replicated all over the place. And every behavior that we'd identified in the requirements statements must be accomplished by collaboration of the objects inside the system. Another technique that is commonly used, it has gotten a lot more play than probably it really deserves, because it sort of falls down when you go to real live situations where you have lots of information that you're dealing with. But is sometimes it's helpful as a way to get started, and it's called noun-verb analysis. What you do is you take all the material that you have and look at all the nouns. So the nouns that people use when they're describing the problem, when you're describing the requirements, you're describing the use cases, whatever nouns that either you use or the problem space people, the customers or whoever, the nouns that you use refer to the things. Right? Nouns are things. And so we can look at the nouns, and from that list of nouns we can identify perhaps the main things in the problem. Okay? Those are the objects. The verbs that people use, these are the operations. When people say, these things happen, functions occur, okay? Those are verbs usually. And so we can identify those verbs, identify the functions that the system has to perform, and then in our OO analysis, we say, well, this function has to go, have to identify which object a particular function has to be associated with. So we sort of match up the functions with the objects. So we match up the data and the related functions to form nice cohesive objects. Okay? So that's the sort of describing it, but it's hard to describe. It's like riding a bike. You can't really describe how to do it. You actually have to try it out. And that's what we're going to look at next.